Hello, this is the next series lecture in organic photochemistry. Last time we have discussed about the Norris type 2 reaction which involves gamma hydrogen abstraction by excited carbonyl, and we have looked into several examples where there is availability of gamma hydrogen and excited carbonyl abstracts the gamma hydrogen to generate 1,4-diradical, and then 1,4-diradical combined to give cyclobutanol as one of the product. If you we have seen that in the case of open chain, in the case of this ketone, aliphatic ketone, where R1 and R2 being these substituents, there is an availability of gamma hydrogen. So this carbonyl undergoes under photolytic condition undergoes type 2 reaction, gamma hydrogen abstraction to give like this, to give 1,4-diradical, 1,4-diradical species. And now this 1,4-diradical have to undergo two pathways. Number one, is the coupling of this 1,4-diradical to give a cyclobutanol as one of the product, or it can undergo fragmentation to give ene as one of the this part goes in the form of ene, and the other part goes as in the form of enol, and which tautomerize to give ketone. So we have 1, 2, 3 products in this one. This is type 2 reaction. This carbonyl also undergoes type 1 reaction as well under photolytic condition, where the alpha bond cleavage takes place to give acyl radical plus other carbon center radical, CH2, and then we have H, R1 and R2. Or it can also undergo this bond cleavage to give a phenyl radical plus C double bond O, CH2, H, R1 and R2. So this is again decarbonylate, and then decarbonylate minus CO to give the acyl radical, and then coupling. So we can expect from type 1 reaction, we can expect phenyl coupling, we expect phenyl, then CH2 and CH, R1 and R2. So we get 1, 2 and then the self coupling of this radical as well. So we have 3 products from type 1 reaction, 3 products from type 1 reaction and 3 products from type 2 reaction. But out of these 6 products, the most important and synthetically useful product is this cyclobutanol is the one of the most important, because we are getting a ring constraint system. The generation of a 4-membered ring is synthetically important because it is a highly strained system, and construction is not very easy by any synthetic route. So by any means, if we can, but in the normal solution phase photochemistry, the yield of this product is very, very low, something around 6%. If we do the reaction in the presence of benzene, toluene, or any cyclohexane and so on and so forth. So by any means, if we can increase the yield of this product, if we can increase the yield of this product, is going to be a very useful reaction, because the most wanted product, the four-membered cyclobutanol, is going to be formed in the material. So any attempt to increase the yield of this product from 6% to maybe 20 or 30% is going to be a very, so people have tried different routes to increase this, the four-member cyclobutanol in the photoreaction of this type of aliphatic ketone. So one of the route which one strategy which has been used is by carrying out the reaction in organized media. The organized media, these are the mediums like cyclodextrin, micelles, zeolites, and liquid crystals, and so on, and other like silica and other materials are known as. So these mediums are known as organized medium because they organize in such a way that they form a very special type of structure. Say for example, in cyclodextrin, the glucose moieties, 5 glucose units, 6 glucose unit, 5 glucose units, 6 glucose units, and 7 glucose units can connect in such a way to give a cyclic structure, or it looks like a bucket like structure or donut like structure. So it can, since it is a cavity like structure, it can, molecules can go inside this cavity and forms host gas complex. So cyclodextrin being the structure being the cavity like structure, it can form host gas complex, so it can form inclusion complex. And similarly, micelles can also form a structure where the hydrophobic and hydrophilic ends can organize to form a globular type structure. Zeolites again is a channel like structure. Liquid crystals can again can have a different type, pneumatic, crystallic, and so on and so forth, can organize to have a special type of structure. So people have tried to use these medium to bring about selectivity in these reaction, and so that we can increase the most useful product, that is cyclobutanol, to an higher yield. Professor V. Ramamurthy has done enormous amount of work in this inclusion complexes to forming a host gas complex, and then study the photoreaction in cyclo. So I am going to just look in two special case where cyclodextrin can bring about selectivity in photoreaction. Similarly, zeolite can also bring about selectivity in photoreaction. So as I have mentioned cyclodextrin, so we'll just very briefly describe the structure of cyclodextrin. So cyclodextrins are cyclic oligosaccharides having a central cavity capable of accommodating host gas molecules in aqueous medium, because cyclodextrins are soluble. So this is soluble in water, whereas the other organic compound like this ketone is not soluble in water, but slowly, just by studying at room temperature overnight, it is molecule, say for example, benzene ring of this ketone can go inside. So beta cyclodextrin, the cavity size is such that it can very well accommodate benzene ring, and molecule can go inside and form host gas complex. So when the benzene ring goes inside, it's just like a constrained medium, and then the free movement of the molecule is restricted, and it can go in it can held up in the cavity, and then it can free movement is not possible, and it can give a particular type of reaction. That what we are going to see here. So we have a most commonly used are alpha cyclodextrin, beta cyclodextrin, and gamma cyclodextrin, where the 6 amylose moieties are connected to each other, to form a circular medium. Here in beta cyclodextrin, 7 glucose amylose units are connected to each other, and similarly in gamma cyclodextrin, 8 amylose units are connected through a oxygen linkage to form a circular structure. The cyclodextrin most commonly used can be, since it is a structure is cavity like a structure, it can form a host system. Can possess a hydrophilic cavity and able to encapsulate a variety of organic compounds in the cavity in aqueous medium. Forms host-jet complex, which we call it as a inclusion complex. The cyclodextrins have a relatively flexible donut shaped structure, where the top of so for example, you have a this is like this. So this is the top of the cavity and this is the bottom of the cavity. So it says that it has a 12 OH groups and out of which six on the top and 6 primary OH groups in the bottom of the cavity. So this is the one the amylose moiety showing, and then it can connect to another 6 moieties and forms a circular trigister. This is the showing that a 6 molecule can connect through this end as well as to this end to give a. So once the molecules amylose units are connected to each other, the structure looks like this. This is the structure of cyclodextrin, where this end can this is the unit which can vary depending upon whether it is a alpha cyclodextrin or beta cyclodextrin or gamma cyclodextrin. And if we look in the actual shape, so it has a this is the structure. We have a the cavity like a structure, or we call it the bucket like a structure. We have a secondary OH groups in the bottom and primary OH groups are heading on the top of the ring. So molecules can very nicely go inside the cavity and get locked, and it can form host gas complex. Lot of modifications have been done in cyclodextrin by making capped cyclodextrin, because both the ends are open. So people have made the capped cyclodextrin so that molecule cannot go once goes inside, cannot pass out from the other side. But that is a different story. We are not going into much detail of this. We are just, at present, our aim is to see how cyclodextrin can form host gas complex and bring about selectivity in any chemical reaction. And here is the case of a photoreaction. Photoreaction of aliphatic carbonyl compound, where there is a possibility of there is a presence of a gamma hydrogen. The excited carbonyl can abstract gamma hydrogen to generate a 1,4-diradical and can give 4-membered cyclobutanol, alkene and acetophenone as 3 products from type 2 reaction. And it can also undergo type 1 reaction by cleavage of alpha bond to give the higher hydrocarbon. So we get around 6 products in total, but the most wanted product, that the cyclobutanol, is in the very low concentration, and that's the idea is how we can increase the 6-member ring, the cyclobutanol, which is synthetically important, and in the from 6-member to in this. And this one of the strategy which is used to study the photoreaction of this carbonyl compound in cyclodextrin. I have just mentioned little bit about the structure of cyclodextrin, and so this is the monomeric unit which combines to give a circular structure, and after combination the cyclodextrin structure looks like this and molecule. So the host gas complex can be prepared very easily just by taking a ketone, that is any ketone where there is a possibility of having a gamma hydrogen. Beta cyclodextrin, this is stirred in water. Cyclodextrin is soluble in water. This ketone may not is not soluble in water, so you can see that if it is solid, it can float on the top of the water, or if it is liquid, and also you can see it in immiscible liquid. So but when we stir overnight slowly at room temperature, the molecule, the benzene ring can go inside the beta cavity, and it can form the host gas complex, and we get a precipitate at the end of the reaction. This precipitate is obtained by once the complex is formed. The molecule goes inside, ketone goes inside the cavity, and it forms its precipitate out, and then which is filtered, washed and washed with any organic solvent, so that any ketone is sticking around the cyclodextrin cavity can wash out, and only the encapsulated ketone is lying in the benzene ring. So this is dried. This is now it is available. This is a ketone encapsulated in cyclodextrin cavity, which is called the host gas complex, is available for the photoreaction. Now you can see here, this is the structure of the host gas complex. You can see benzene ring has nicely gone inside the cyclodextrin. This is a cyclodextrin cavity, and now once the molecule gone inside, it has now it is in the constrained medium, and it has a restriction in movement. It cannot move, and hence when we irradiate, the caramel gets excited. Excited caramel has more probability to abstract this gamma hydrogen. This is alpha, beta and gamma hydrogen. And so whereas if the molecule is not in the cavity and it has a free movement, so it has a less probability of abstraction this gamma hydrogen, because molecule can be of this way and so on and so forth. But once the molecule goes inside the cavity, it has now it is in the constrained medium, it has a restriction in movement, and hence it has a better chance for excited caramel to abstract this gamma hydrogen to generate 1,4 diradical, and then this 1,4 diradical can combine to give cyclobutanol as one of the product. But of course we cannot rule out other possibilities, such as gamma hydrogen, the alpha bond cleavage, that is type 1 reaction, and as well as the cleavage of the fragmentation of 1,4 diradical gives alkene. But it has a better chance to abstract gamma hydrogen and then to generate a radical, and then so it has been found that when such ketone where there is a availability of gamma hydrogen, it is encapsulated in cyclodextrin, is in constrained medium, there is a restriction in movement in the molecule, and hence because it is locked in the cavity, and it has a better chance to abstract gamma hydrogen, and once it is abstract gamma hydrogen generate radical and can combine to give. So by doing this, it is possible to increase the yield of the product from 6% to 29%. So it is a really great achievement in bringing out selectivity in the most wanted or most useful cyclobutanol product, which is very difficult to constrain because it is under highly strained system. And so the yield from normal solution phase photochemistry, it has increased to 29% yield when it is irradiated in the by forming the host gas complex, where the molecule goes inside the cavity, and after that the cyclodextrin, and then it can, of course, workup can be done by extracting with the dissolving in water, where the precipitate gets dissolved and extract with organic solvent, and then we can recover the cyclobutanol product. So hence we can see that the cyclodextrin brings about selectivity in photoreaction, and this is an example of the organized media such as cyclodextrin can bring about selectivity by increasing the most useful product cyclobutanol from 6% yield to 29% yield. And like this, several more examples have been studied. This is one of the representative example where we have shown that the selectivity can be brought about, and it is possible to get to divert the reaction to our choice and to get the desired product in more yield. This is another example where this is a case of a you can see this is the zeolite channel. The molecule can nicely goes inside. So this is again a ketone has gone inside the zeolite channel, and there are ways to make this molecule in the inclusion complex, to bring the molecule in the cavity and bring the molecule in the channel. So once the molecule is in the channel of cyclodextrin, and when we irradiate the molecule carbonyl gets excited, and it can abstract gamma hydrogen. This is alpha, beta, and gamma hydrogen can generate a 1,4 diradical. So 1,4 diradical here, but if it is not in the channel, now you can see that the carbonyl compound is in the cyclodextrin cavity, cyclodextrin channel, and it has a restriction in motion. There is no molecule is constrained in the medium. It has not free rotation. It is not possible to make free rotation. But if it is not in the cavity and is not in the channel, this molecule can of course can go around, and the probability of abstracting gamma hydrogen would be less. But here, once the molecule is in the constant medium, it has a better chance to abstract gamma hydrogen to give a 1,4 diradical, and this 1,4 diradical can combine, can react to give a cyclobutanol, as well as it can fragment to give these two products, this alkene and the carbonyl compound as well. So so here, whereas if we do the reaction in the constant medium, it is possible to bring about, whereas if it in the solution phase, the yield of this product is very low, but here it has once it is in the constant medium, it is possible to increase the yield. This is another example of the molecule where is a macromolecule. It is again a carbonyl compound. It is in the cavity of zeolite, in the channel of zeolite, and under photolytic condition, it can it can undergo the alpha bond cleavage, can undergo alpha bond type 1 reaction, and then this type 1 reaction, and then it can the radical can once again can combine and to give a another product which we can see here. So open cyclic system inside the cavity can give another product in the cavity, and you can see here the molecule is now it is connected with the para position. So these are the two examples where we can see that the organized media such as cyclodextrin, zeolites can bring about selectivity in the reaction, and which is not possible if we do the reaction in normal solution phase photochemistry, or if at all it is the product is formed in very low concentration. But these the medium bring the molecule, and there is the constant medium restriction in motion, so it is forced to undergo this type of reaction to give the product in good yield. Going further, initially when we start with, we have mentioned that the carbonyl compounds can undergo 4 different types of reaction. Type 1 reaction, Norris type 1 reaction, which involves alpha bond cleavage. Type 2 reaction, which involves the gamma hydrogen abstraction, which we have been discussing just now. We have also discussed to bring about selectivity in gamma hydrogen abstraction to get the cyclobutanol product in more yield. And also the third type of reaction is the photoreduction. This photoreduction is a third class of carbonyl compounds. It is very it is very common in aromatic ketones like benzophenone, where the in the presence of light, this can undergo goes to an excited singlet state, and this benzophenone has very susceptible to undergo to excited triplet state. These excited triplet states are nothing but they are diradical species, and when one to dialectical species is formed, it can abstract it can abstract gamma hydrogen. It can abstract, O radical can abstract hydrogen atom from the solvent. This is the abstraction of hydrogen atom from the solvent can rate this, and this radical can combine. This radical can couple to give a diol as one of the product, as well as this can recouple to give this. So these are the, essentially, if we can see overall photoreaction, the carbonyl compound gets reduced to the CHOH, or it can also form the dimeric product. So the under photolytic condition, aromatic ketones can undergo reduction to give a diol as one of the product, as well as CH reduction of the carbonyl as another product. This reduction can also brought about by under photo-induced electron transfer reaction. Here we can see this is the indinone, and in the presence of light, this triethylamine is also used as a electron donor and isopropanol as a solvent. So if we do the reaction under photolytic condition, this in the presence of light, there is an electron transfer from triethylamine to carbonyl compound. So triethylamine acts as a donor, this carbonyl compound acts as an acceptor. So it is like a donor acceptor photoreaction, donor acceptor photoreaction. So triethylamine donates an electron to carbonyl compound to give this radical anion, and triethylamine goes as a radical cation, and this radical anion can abstract a hydrogen atom from the solvent to give H plus. This O minus can abstract H plus from the solvent to give this. This may undergo coupling, this radical coupling, to give a diol as similar type as we have seen here. This type of diol can, indinone diol can be formed by coupling at this end, as well as this can abstract an hydrogen atom from the triethylamine, the CH2 of the one of the CH2 group of ethylamine can abstract hydrogen atom. So we can see overall this is a photo-induced electron transfer reduction. So reduction of carbonyl can be possible, mostly common in aromatic ketones, possibly on direct photolysis, as well as via indirect photolysis, where in the presence of triethylamine. This is a case of photo-induced, homogeneous photo-induced electron transfer reaction, where triethylamine acts as a donor and indinone carbonyl acts as an acceptor. In the presence of light, triethylamine transfers an electron to carbonyl. Carbonyl becomes radical anion, triethylamine becomes radical cation, and then O minus abstracts a proton from solvent to give OH, and then this can give these two products as a reduction of. So overall, the reduction of carbonyl takes place from carbonyl to CHOS. So it is possible to reduce the carbonyl both under direct photolysis as well as under indirect photolysis. So we stop here and then we'll continue on the next lecture. Thank you very much.